Hello, we are ME23 for Penn State Barron's Senior Design Mechanical Engineering Capstone Project. Our project was the once-through steam generator flow restriction device. Our team included Lucas Rodgers, Shane Rupert, Toby Williams, and Nevin Rutherford. Our sponsor was John Cockerell's Energy Division, which focuses on the creation and design of heat recovery steam generators. Now, a heat recovery steam generator takes excess waste heat from a gas turbine to then boil water to be turned into steam to run a steam turbine. This helps to create even more electricity when that heat would have just been going to waste otherwise. So for our design, we are putting our restrictor on a once through heat recovery steam generator. Now, a once through takes pressure and water in from one end, boils entirely within the tubes, and goes out the other end. Now, the issue that arises with this, since there's no separation between the steam and the liquid, this can create two-phase flow, particularly with the uneven heat from a gas turbine. So, in two-phase flow, the pressure drop versus flow rate becomes unstable. This can cause certain tubes to hog more liquid than others, causing other tubes to then dry out and start oxidizing or just being at a higher temperature, which creates cracking or fatigue failures. So with our flow restrictor, our goal is to push the create an external pressure drop right at the beginning of the tube that is passive without any active control to keep the liquid entirely in the single phase flow region, which keeps our pressure drop and mass flow rate consistent and predictable. We generated many designs, but these three designs in particular are what stood out to us. First is the plain orifice, which is generally what's standard in industry. So all of this is the water comes in from one side and there's a pressure drop across it. The helix restrictor works off of the principle that water will have friction with the sides of the tube by artificially increasing the length of the tube with the helix. Then there will be more friction loss and more pressure drop across its entire length. The offset orifice works the same as on the same principles as the plain orifice, but may have an added pressure drop from the offset holes. Our final choice was the offset hole rotating orifice. Now, we had empirical calculations that were designed particularly for a plain orifice. Since this works off of the same principle, we figured we can use those equations to get an idea of how much pressure drop would be across each plate. Now, the issue comes in with the geometry changes between each plate, such as the spacing or the offset. How much does that pressure drop get affected by this geometry instead of just a plain center hole orifice? So we decided to do analysis using CFD and FEA. In CFD, our sponsor provided flow conditions to see how the geometry gets affected, how the geometry affects the pressure drop. With this, we decided to go with a three-plate design, which will provide just enough pressure drop that is required by our situation. Due to the very, very high turbulence in between each plate, we decided to use the K omega equations, which works better in this higher turbulent region. For our FEA, we decided to test thermal expansion from an off cycle to an on cycle without any water running through it. Now, these are the most extreme conditions that our restrictor will undergo inside of the recovery steam generator. During proper normal operation, the range of temperatures is much more limited, but this is a worst case scenario. So we tested the thermal expansion to try to get the thermal stress and fatigue. After testing, the stresses caused by thermal expansion do not create cracking failures or fatigue failures with our chosen material. We also decided to manufacture actual orifices to be tested on a testing rig. This process took bar stock milled on a lathe to then be tapped in the middle with threads, which with each orifice plate being put on a threaded rod and spaced with spacer rods that went over the threaded rod. And to make sure that we kept the orifices at the exact proper angle, we added small spacers of copper wire to make sure we kept that 180-degree separation between holes. These then full assemblies were pressed into our test section to then be later tested. Overall, we tested 6 different geometries, all with differing spacing, hole sizes, and number of plates. Here is a video now of our manufacturing process. That manufacturing process only showed us creating one of the plates, tapping the center hole where our threaded rod would sit that supported the plate. Our plates were then brought over to a Haas machine to have the outside rim where the O-ring would sit and the center hole in which the hole for the orifice where the pressure drop is created. Now for our testing, here's the testing rig. This was designed and built at John Cockerell's facility. Each of the sections shown on the right has our different orifice geometries. Through this testing, we checked different flow rates, and through our data acquisition system, we were able to find the pressure drops of the different flow rates for each different test. We tried to vary this flow rate as much as we possibly could. Now, some designs that had higher amounts of flow restrictor or a higher predicted pressure drop only could provide a certain amount of flow as the resistance increased with the amount of pressure drop. Through this, we were able to create 2 different curves. One was a tested pressure drop prediction curve with our data acquisition system data, along with a calculated value to then make a curve to predict our flow rate outside of regions that we were unable to test. On the right side, we were able to create curves that used our empirical calculations to predict how the flow rate would change with varying size orifice geometries, and diameters. This gives us a comparison of how we can adjust our actual test data to then create an Excel tool, which will be able to calculate any geometry, any spacing, and its respective pressure drop. For our final design, very similar to our testing rig, we have the offset orifice plates, but on top of this, we will create a sheath, which is shown on the right, for our orifices to sit inside of. This sheath provides much better geometry than the actual HRSG tubes, which can have a lot of variance in them. If we use this sheath, we can ensure proper sealing so that liquid doesn't flow past the restrictor, and we can also vary the geometry of the sheath to help increase or decrease the amount of scalability required for each individual HRSG.